Hey guys, Miss Gray. So we're gonna go over homework number 3, so week 3. And we're gonna start with I want to just kind of review quickly last week's topic. So this week's topic starts with 6.6M, but and that's what I have on the screen here, which is finding rate from a graph. But I do want to remind you of last week's topic, which is 6AV. So if you haven't done it yet, maybe this is a good reason to do it because you watched me do it and it seemed easy, which was finding a rate from a table. So these are basically the same idea. It's just 2 different representations. So let's review this one by looking at the example over here. So if I'm looking at the rate of change between 2010 and 2011, actually, you know what, let's jump forward and do a harder one just so that we can convince ourselves that we know how to do it. So 2009 to 2012, so in that table, I'm literally only paying attention to those 2. And then 21 is 2009 and 30 is 2012. So the rate of change for this kind of linear relationship is the change in y over the change in x. So you're always comparing what's happening with the y's in a fraction over what's happening with x. So it's like a division problem, but we want to look at it as a fraction. We like this when it's a fraction. So if I'm looking at this side, the changing part is going to represent the change in y here. And this side is going to represent what's happening with the change in x. And that's what's happening from here to here and from here to here. So for the y's, to get from 21 to 30, I have to add 9. And then for the x's, to get from 2009 to 2012, I have to add 3. And really, I'm just setting this fraction up with these 2 numbers, right? So the change in y is 9, and then the change in x is 3. And so when I simplify this fraction, it becomes 3 over 1, which is just 3. So that's what the rate of change is here, is 3. If I go now forward to what we're doing this week, oh, look how much writing I did on this side. So this rate of change idea, though, still works for this here, too. The difference is that here I'm not looking at a table anymore where it just lists the points. I'm looking at a graph where I have to pull the points out. So the extra step here is I am doing the same thing as this, but I have to get the points first off of the graph. So if it's telling me to look at 2005, 2006, that means I'm still going to be comparing 2 sets of numbers like this. So I can fill in my table like that and just read what they are off the graph. 2005 is 11. 2006 is all the way up here at 15. So again, if I'm checking that change in y, I'm going up 4. So my top number here is going to be 4. And then here I'm going up 1. So 4 over 1, which is just 4. So it's 4 vacations every year. All right, same thing for this example. I'm going to do this time 2007 and 2010. So reading them off the graph, 2007 is 12 and 2010 is 9. So this time when I look at my change in y, I'm going down this time. So I represent that, obviously. Hopefully that seems straightforward with a -3. And then this time I'm going from 7 to 10, which is a +3. So if I put -3 on top and +3 on the bottom and reduce this, -3 divided by 3, oh, oops, then you have -1. So basically, according to the graph, the rate of change is it's going down 1 game per year, which I can't put positive, so be very careful. If you put 1 game per year, it's going to count it as a positive, a plus game per year. So since we want to do negative, we have to put a negative sign to show that it's going down 1 game per year. So be careful. I would say that one of the biggest errors here is sign mistakes. Just make sure you're paying attention to things like, is it going up? Is it going down? Okay, so from here, we move on to What happens if you have a constant rate? So on these graphs, we had a changing, it was changing each time. So basically you're kind of looking for almost like an average between two different things. Whereas when we get to here, we're just looking at one situation that has a constant rate of change. So the idea of trying to find, so this is topic Z, E, F. Here you're still trying to find a rate of change, which now we're calling, because it's constant, when it's constant, we call it slope. So now we're saying we're trying to find the slope of this line because it's the same no matter where we are at, but it's still that same idea. We're literally doing the exact same thing. We're looking at it and saying, okay, from here, this point, right? So if I was going to make a table, I could do that. So I could say, well, there's a point here at 0, 2. And then it looks like there's another point here at 1, 6. So I could go through and do the change in y is a +4, and the change in x is a +1. So slope, which we call m, so I'll label this. So you'll see this lots of times throughout the years. So slope is, we call that m, is going to be the change in y, right? Change in y over change in x, just like always. So 4/1. So 4 in this bucket. But the other thing that's nice about this is you can also look at it on the graph and count it. Because remember, the other idea of this change y over change in x is that it's rise over run. And you can see that on the graph. And so that's kind of nice with the graph, is that it's a little easier. So it's the same idea as what we were doing before, but there is an easier way to do it, which is just to count the boxes. So if I'm standing here at 0, 2, like I had put in my table, and I just count how many boxes I rise and then run, I'm really going up 1, 2, 3, 4, and then over 1. So 4/1, which we can just say 4. If you put over 1, it'll still count it. So like on this one, if I want to just count them, I could say, well, I'm starting here at the 70, right? And then I'm going to go up 1. Which counts as 10. So slope here. So I'm going up 1 box, which counts as 10. And then I'm going over 2 boxes, which counts as 20. So if I reduce that, it ends up being 1/2. Oh man. So the other good piece of advice that I can give to myself as well is make sure you read the instructions. So even though our answer is correct, they want it as a decimal because they want it listed as numbers, right? So they're really saying that this is 50 cents or half of a novel per dollar. So be careful. Got it. All right, so let's try again. So if we go through here and I look here, right, 10. So if I'm standing here at the 10 and I want to go to the next point, it looks like it'd be there. So I have to go up 1, 2, 3, which from 10 to 40 means really I'm going up 30, right? And then I'm going over 10, 20. So 3 over 2. Okay, something happened with my video, but basically, it moved forward. But basically, this 3/2, 3 divided by 2 means it's like $1.50. So when you're entering it in, it'd be 150. For this one, same idea, right? So M here. So I'm going from 0.20 up to 10.50. Which if you're looking at it like that table, I think that's an easy way to see, that this is going to go up 30 and then up 10. But if you're counting, you can also go through and say, okay, well, if I'm standing here at 20 and I go up 30, 40, 50, So I went up 30, rose 30, and then went over 10. So you just have to pay attention to what the units are mostly, like how big each unit block is. For this one, I am starting here at 10. So I have to get from here up to here, so not very far, right? So I have to go up 2 blocks, which is 10 each, so that's 20, so up 20, and then over 10. So 62. Okay, so I don't think these get that much more difficult than this. I think it's just more practicing with it. So here it starts at 5. So this one you can just count, right? Because it's by ones. And it goes up here to this point. So it goes up from 5 to 7. So up 2 over 1. So this would be 2. Well, hopefully it'll get easier as you practice more. Okay, the second half of this kind of week of stuff. So this first part was figuring out rates of change from graphs, basically. And then the other part is making sure you understand the difference between linear and nonlinear. And linear and nonlinear is a pretty straightforward idea. So the word linear has the word line inside. Because if it's linear, then it's a straight line. Except vertical lines. So the only one that's not considered linear is a vertical line. So one that's straight up and down. So that's the only straight line that's not considered linear because it doesn't pass all those kinds of tests and things. But the rest of them, it's fine. So like this one, nonlinear, not straight. Linear. So hopefully this seems pretty easy. Linear. Nonlinear. Ooh, so linear, right? It's going to make a straight line. This is definitely nonlinear. So it's really, honestly, the difference between being straight or not straight. Ooh, okay. So now we need to look at whether it is linear or nonlinear from an equation point of view. So basically, if you have y equals, and it's in this form, where this is a number and this is a number. So this has just some random number here, and this has some random number here. For example, y equals negative 8x plus 5. So it has y equals a random number, x plus with a random number. So that fits this form. Basically, x has a power of 1. There is no other power. So x has a power, an exponent of. So that's one way to tell. So this is linear. This is not because x is on the denominator. So x also has to be like on top where it's like on a normal situation, whereas here you're dividing by x in this example. So x in denominator is not linear. So non-linear. This is linear, so it has x power 1. Perfect. Ooh, x has a power of 2, non-linear. X has a power of 3, non-linear. X, normal by itself, power 1, not on the bottom. Looks pretty linear, so don't let the fraction throw you off. This, no. So no square root over. So you can't have basically anything unusual. It just has to be an x with no exponent and just on top of the fraction and then normal with a number or maybe no number. So this is nonlinear. Ooh, y equals 6/5. So we'll talk more about this later, but this has x. It just has 0 x's. So really, if I was going to rewrite that one, y equals 6/5, I really could say it has 0x plus 6/5, which is still fine because it's not in the bottom. There's just nothing. It'll make a straight line. It makes a line that looks like that. For horizontal because there's no slope, no rate of change in front of x. So it's still linear. This one, even though it looks a little complicated, I really could rewrite that as y equals -1/9 x plus 7/4. And so since that's really just a regular x, it's on top of the fraction, basically, it's linear. Non-linear. Linear. Ooh, here I go. Let's see if I can do it. Ooh, top of the fraction, power 1, looks pretty linear. Ooh, power 2, no way. Power 1. Exponent? No way, can't be in the exponent either. Bottom of the fraction. Top of the fraction, power 1. Square root? No way. 0x? That's all right. X top of the fraction, power 1. Oh, dun 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 dun. I did it. I earned a gold medal. All right, so if you're looking at this situation, you're really kind of looking for the same type of thing. But now for topic VGS, you don't have a graph. So one thing you could do is you could graph it, right? You could go through and graph them and see. Probably the easier, or at least I think the easier thing to do, is just to look at the change between them and really what you're looking for. Remember why we talked about this idea of this constant rate of change? Because if it's linear, it has a constant rate of change. It has a slope. So it has to have a constant rate of change, which basically probably in your mind just sounds a lot like a pattern in the table. You're probably thinking of it kind of like what you would see in a pattern from math you've done before. So it's like this side goes up by 1 each time, right? So that seems like it goes in a pattern. Whereas 19 to 10 goes down by 9, but then 10 to 2 goes down by 8, which is not a pattern, which means this is non-linear. So that's really what you're looking at, is does it have that constant change? This goes up 4, 5, 6 by 1 each time, right? So 18 to 13 is 5, and 13 to 8 is 5. So since they're both in a pattern, same rate of change. 7, 8, 9, so each goes up by 1. So 11 to 8 is 3, but 8 to 4 is 4. So nonlinear, not a constant change. So you're looking for a constant change. This one, 0, 1, 2, and then 11 down to 3 would be -8, right? You're going down 8. But then 3 to 2 is just -1. So that definitely is not the same rate. 16, 17, 18, so that goes in a pattern, but 3 to 12, so that goes up by 9. And then 12 to 19 goes up by 7. So a lot of these are not fitting the pattern. All right, so this one is where it gets a little bit more complicated. So now you have to make sure you're kind of tracking both sides, because sometimes they could give you fractions that look different, but are actually the same. So let's double check stuff here. So this side, x's here, 5 to 11 is going up by 6. 11 to 17 is up by 6. This 15 to 12 is down 3. 12 to 0 is down 12. So nonlinear. So you just need to make sure as you're going through these that you're checking. So -7 all the way up to 1 would be +8. 1 plus 8 here would also be 9, right? Oh, no, I put it backwards. 4 plus 12 here is +8. And 12 plus 20 here is +8. So really this reduces down to 1, right? It's going up 1 over 1. So this is linear because both sides are the same. So +8 plus 8 plus 8 plus 8. Since everything matches, this is linear. So hopefully that makes sense. just be careful to go through the table and make sure you understand how it's changing. Okay, I think that should probably be enough to get you moving through your homework. So good luck.